Thank you very much, Miranda, for the introduction. Very nice to meet you all here today. I'm personally very excited to be here because I'm a mom for a 2-month newborn at home. That means in the last thanks. That means in the last 2 months, I have been mostly facing 3 more people in the family. But today I have more than 3, probably 300 people. So that's on the one hand very exciting, but on the other hand, please bear with me if there's any hiccup in the presentation, because it feels like I'm learning to enter a big society again. You might have noticed that the title of my presentation has been slightly changed. So the key information I'd like to share with you won't be changed. Still mostly focusing on the perovskite silicon tandem solar cells. But I just added some more information in a way that I'm really hoping that the content here I pass to you would be not only having sufficient depth to those who have already experienced in the perovskite or the PV field, but also providing sufficient information to make the content more easily accessible for those who haven't been doing the research in the perovskite silicon tandems. With that, I'd like to go ahead for introducing the technology. I'm probably sure that majority of you are aware of the perovskite material, which has been a hot topic in the last decade. So for those who are not familiar with, the perovskite has a molecular structure of ABX3, so with a crystal structure on the top left. So where ABX all have a variety of choices for different elements. For example, X, we can have iodine, chloride, bromide. Or for B, we have lead and other metal ions. And for S side, we have different element as well as some organic groups, such as methylammonium and formamidinium, cesium, and also rubidium. So with this possibility of varieties of elements in all the different positions, there is also a large family of the perovskite material that has been tested and proven to have good performance in the application in PV, including some other optoelectronic devices. And also because of this, the perovskite group material has also an advantage of flexible tunability in a large bandgap range, down to 1.2 eV and up to 3.0 eV. So for those who work in the PV field, that is very, very important, because that means this material can be not only useful for the single junction perovskite solar cell, but also can be applicable for the tandem solar cell designs. Beyond this, the perovskite material also have a few critical exceptional optoelectronic properties that allow the material to be performing exceptional in the solar cell field. So these include the very high absorption coefficient and very long carrier diffusion length, up to a few hundred micrometer, and also a very high defect tolerance. So all this allows the perovskite material to deliver very high performances in the both the single junction cells design and as well as a tandem design. So in the following, I just show 2 groups of pictures showing the different morphology of the perovskite material. So not only the perovskite composition has a lot of different possibilities, but also the morphology can be not only multicrystalline, but also single crystalline. And both of them have been achieving high performances, and particularly for the multicrystalline perovskite, which has been leading the record efficiencies and has been mostly used in the majority of the high performance devices. So I have been mentioning high performance for the perovskite material, and so this picture here, which shows the efficiency evolution of the perovskite, single junction perovskite solar cell, shows a clear picture of how the perovskite is progressing in the last decade. As we can see, just around a little bit over 1 decade ago, the efficiency starts from certified efficiency started from under 15%, and now is already achieving 27%, which is on par with that of the single junction silicon solar cell. Although I need to note that the cell area here for the perovskite is much smaller than that of the silicon. The cell area that is used for the perovskite is just around less than 1 square centimeter. Some of them is only 0.01 square centimeter, which is way smaller than that of the silicon solar cell. Of course, that is much smaller than what we require for the commercialization requirement. Okay, so beyond the versatility in the perovskite material compositions and their morphologies and the way of how to make them, there are also different types of device structures that have been investigated and also proven to having demonstrated high performances. And on the slide here shows the two types of typical single junction perovskite solar cell structure with different polarity. The yellow arrow shows where the sun illuminates. So when the sun illuminates from the electron transport material part, that structure, we call it NIP perovskite cell structure. On the opposite, if the sunlight illuminates from the whole transport material, that cell structure, we call it PIN cell structure. So both of the cell structure have been intensively researched and also have shown high performances. And both of them having, for example, for the single junction, both of the cell structure have shown over 26% efficiency. Okay, just to give you a little more detail about how these two types of material are built and what are the material that are used. Take NIP cell structure as example on the left. So we use FTO as a substrate. On top of it, we use metal oxide, tin oxide as an electron transport material. And then we have the whole transport material used based on organic materials called spiral omitide. Of course, we have other alternatives like PDA and some other alternatives that are also efficient and stable. And the perovskite material is sandwiched between the two materials, and the light is illuminated from the bottom, from FTO side. So that's a single junction NIP perovskite solar cell. So that's one of the structure we at NU, our group have been research for around 1 decade, and one of the typical IV performances is shown here, which is one of the high performance we recently achieved in the last year, where we get over 26.2% efficiency from the reverse scan. That represents one of the highest efficiency based on the same structure. Of course, the PIN cell structure have also achieved high performance, but the cell structure is different, and also the material that have been used are also quite different. As you can see that we start from the whole transporter material, some of the using the pure self-assembling molecular SAM, or the bilayer of the nickel oxide SAM as a HTAL, whole transporter material, and on top of it is a perovskite. To finish the cell structure, we have the carbon-6 BCP, again, the organic material to allow the low temperature processing on top of the perovskite without a damaging material, because the perovskite is relatively sensitive for the temperature. So with that, we also achieved, example is that by using some new SAM material, we were able to achieve 26%, 7% efficiency. Given the time, I won't dive too much into detail, but I would like to move on to the tandem, because high-performance single-junction perovskite solar cell is a key to achieve, to contribute to the achievement of the tandem cells. Okay, so single-junction perovskite high performance is very attractive, but I guess also personally, I think its capability of enabling high performance of tandem is even more attractive and important, given the efficiency limitation of the single junction solar cell and also the silicon solar cell, which is limited to 27%, which we will see later in my slides. So the perovskite silicon tandems, no matter what cell structure is, whether it's 4-terminal, 2-terminal, or even 3-terminal that has been recently researched a lot, have the potential of achieving efficiency of over 40. And for those who haven't been working on the tandem too much, here the structure of the tandem in 4-terminal on the left and the 2-terminal on the right. So the major difference of the 4-terminal and 2-terminal is the integration of the two cells, whether they are having the electrical charge diffusion directly. For the 4-terminal tandem, there's only optical coupling between the two subcells, but there's no direct electrical connection of the two subcells. As you can see, the two cells are separated with both the transparent contact of the top cell of the back of the top cell as the transparent contact of the top cell in the silicon cell both present in the cell structure. But for the 2-terminal, the cell structure is simplified by removing one transparent electrode here. Instead, there is an interconnecting layer that connects the two cells electrically. Okay, so the potential of the high performance for the perovskite silicon tandems have been proven. And as you can see, this efficiency revolution again for the perovskite silicon tandems over the past decade, both the 4-terminal and the 2-terminal tandem have achieved efficiencies that are well beyond that is achievable for the silicon solar cell, which is 29.4%. So initially, the 4-terminal tandems have been more researched and have shown higher performances, but in the recent years, the 2-terminal tandems have shown higher efficiencies and laid the record efficiency. And one of the reasons, but not the only reason, is the 2-terminal has more streamlined cell structure. One of the reasons I mentioned just now is that less substrate used in the cell and less TCO used, transparent conductive oxide in the cell, so less optoelectronic losses in the cell structure. Okay, so going forward, I would like to introduce you a little more of our thoughts and designs for making efficient and stable tandem solar cells, and take 2-terminal tandem as example. Here, this is an illustration of the structure of the perovskite of a 2-terminal tandem structure. Obviously, it's very important and straightforward to develop the efficient and stable both the top cell and the bottom cell, which is the perovskite solar and the silicon solar cell, respectively, in this situation, to allow us to make efficient and stable tandem. But that's not the only thing we need to do. There are many more other aspects we need to consider. One of the important things is how we integrate the two subcells into one devices. So that means the interconnect layer that is not only optically transparent, but also resistivity point is very conductive for connecting two cells. Beyond that, of course, the electrode are very important for any type of cells. For the tandem, the particular requirement is the transparency of the top electrode, and as well as the stability, particularly for the perovskite application. Given the time today, I will more focus on introducing you 3 aspects we have done to improve the efficiency as well as the stability of the perovskite silicon tandems. These are the perovskite top cell and silicon bottom cell, as well as their interconnect design. Okay, let's start from the perovskite top cell. For the most used perovskite top cell, The band gap has been mostly locating at 1.65 to 1.7 eV. That's because this is modeled to have the highest efficiency at the standard testing condition particularly for the monofacial perovskite silicon tandems. But if we look at the performance of this wide bandgap perovskite 1.67 EV here in the chart, compared to that of the lower bandgap 1.5 or 1.55 EV, we can see that the efficiency lags much behind that SQ limit. As you can see, the VOC loss of the wider bandgap is more than 100 millivolt versus just around 50 millivolt for lower bandgap. In terms of fill factor, absolutely, we can see that the wider bandgap perovskite, there are rare reports showing the fill factor of above 0.85, but there are a handful of reports showing fill factor of low bandgap perovskite of above 0.86, some of them achieving 0.87, which is very beautiful. So with that, although there are a lot of progress in the last years for the perovskite, wide-band perovskite, but there are still a lot of space to further improve. And one of the reasons for limiting the wide-band perovskite solar cell efficiency is the non-satisfactory perovskite morphology. For example, when we use some commercially used SAM material like 2-packs, so there will be usually, we tend to see large voids in the perovskite film if the perovskite process is not well optimized. So this will leave a large recombination channels for the cell, thus very, very detrimental for the cell performance. And also, the energy level between some of the widely used SAM, here, 2-packs, as I mentioned earlier, doesn't have perfect or ideal energy level alignment with the perovskite, particularly for the wide-banding perovskite, where the energy levels shifts compared to the lower bandgap perovskite. For example, the valence band is going deeper compared to the lower bandgap. Therefore, there is a necessity to engineer the charge transporter materials that work together with this wide bandgap perovskite material to allow high performances. So one of the strategies we have designed and tested to be successful is to use a hybrid or mixture of the SAM material. For example, we used the commercial 2-pack again as a base, and we added the ME4-packs, another commercial widely used SAM material, which allows us to tune the energy level in a way that reduces the energy offset with the perovskite, so that we allow not only efficient charge transport between the perovskite and this whole transporter material, but also reduces the energy loss. In the meantime, because of the use of this mixture of the SAM, which allows us to achieve more uniform whole transporter materials and also increased wettability, so that we also achieve the even better perovskite films. That allows us to have, such a complete and higher quality perovskite film without any voids. So this allows us to not only improve the VOC, but also simultaneously improve the fill factor, which has been a challenge for the perovskite solar cell, because usually when we want to improve the VOC, we adopt the passivation technologies like using 2D perovskite material or inorganic material that usually are not conductive, so that usually the VOC enhancement comes together with the sacrifice of the fill factor. But here, the achievement of the simultaneous improvement of the fill factor and VOC, showing that this hybrid combined mixture of the SAM is a very effective strategy to help us to improve the performance of the perovskite cell. And we then achieve high performances, and particularly when we compare our fill factor with those reported results, we achieve very high fill factor of 86.8, that is certified by CSIRO. This reduces the, again, you remember that the fill factor loss of the wide band gap was 5.5 compared to 4.8, if my memory is correct. But now it reduced down to 3%, around 3%. So that proves that this strategy is quite effective, and such a wide bandgap perovskite is integrated into the four-terminal tandem to demonstrate compatibility with silicon for tandems. And by using a TOPCon cell, we were able to achieve around 31% efficiency four-terminal tandems. So this strategy not only is applicable for the four-terminal tandem, but also can be used as two-terminal tandem, which I will talk more going forward. Okay, so I've introduced some of our consideration in the design of the perovskite top cell, and moving on, I will also mention about our thinking about the silicon bottom cell selection. For the four-terminal tandems, the use of the silicon, what kind of the silicon bottom cell to be used is probably less, is more relaxed because there's no electrical connection between the two cells. But for the two-terminal, it's more strict because we want the two cells to have the efficient electrical connection, so that the IBC won't be, apparently it won't be used easily integrated into the two-terminal, but the other cell structures, particularly the passivating contact silicon cells like TOPCon and silicon heterojunction, are both very compatible and also have delivered a high efficiency for the two-terminal perovskite silicon tandems. And it's still an open question which subcell, which silicon cell will be more suitable, or maybe have the better future for being used for the two-terminal. But in the following are some of the key aspects we consider when we started the research on this direction around 8 years ago about which solid bottom cell to use. So first is first aspect is market share. So we know that TOPCon is now dominating the PV market share, and probably will be still dominant in the next decade. Of course, silicon heterojunction will also increase the market share. So that's one factor to consider, but also importantly is efficiency. The TOPCon and the silicon heterojunction both have achieved, so the TOPCon solar cell have achieved very fast progress in the past few years, making the efficiency in single junction very close to that of the silicon heterojunction. And this is not only true for the single junction, but also for the tandem. So this chart shows the evolution of the two-terminal tandem efficiency with different silicon technology. So this efficiency collects from efficiency chart as well as some new news media news. So it probably won't be complete, but it covers the majority of the key breakthroughs in the field. So the perovskite TOPCon tandem research is much later than that of the perovskite heterojunction, but the past 3 years have seen very fast progress. And ANU was was the first to report the perovskite TOPCon tandem in 2018, and now the highest efficiency for both schemes were achieved by two leading companies, with Longi achieving 34.9%, probably now 35% for silicon heterojunction perovskite, and also Jinko recently announced 34.8% for perovskite TOPCon tandem. Okay, of course, cost is essential, and the TOPCon cell has clear cost advantage compared to silicon heterojunction, particularly for the CapEx advantage. And in terms of the application tandem, cost analysis also show that perovskite based on perovskite TOPCon tandem shows potential for lower cost. Okay, given the time, I will go quicker. So the stability of the TOPCon, particularly the thermal stability, is also better than that of the silicon. The TOPCon can be stable above 400 degrees. That will be very helpful for us to employ different types of the material as well as different type of perovskite cell structures into the tandem. So therefore, it allows us more flexibility to achieving and develop high performance cells. Of course, the other important is sustainability. TOPCon uses less critical materials like silver and indium, so that it allows the cell structure to have a higher production capacity given the limited global supply of these critical materials. Okay, so ANU first reported the perovskite TOPCon cell based on NIP perovskite cell structure, as you can see here, as using the P plus poly as the emitter. And we were able to achieve 24% efficiency back in 2018. And then we, in collaboration with our industry partner, Jinko Solar, we also demonstrated the high-performance perovskite silicon tandems based on mass-produced, commercialized TOPCon silicon from Jinko's production line. And over the past 8 years of collaboration and through extensive electrical and optical optimization and engineering, we were able to, at ANU, we achieved in-house over 31% efficiency perovskite silicon tandem based on planar TOPCon. And of course, I mentioned that Jinko has announced over 34% efficiency on textured TOPCon silicon cells very recently. Okay. Till now, I've also mentioned the perovskite top cell. I've mentioned the silicon bottom cell, and I also mentioned that interconnect layer is also very important. And going from 4-terminal to terminal, we reduce the transparent interconnect layer from 2 TCLs to 1 TCL, and going for we take another step forward and further remove this TCL in a way that we made a very innovative interconnect-free perovskite silicon tandem. And so this structure is very attractive because it not only simplifies the cell structure, but also it enables high efficiencies. So the high efficiency have been proven, and we, through, again, improvement of the both subcells. For example, we implemented the double-side polysilicon into the tandem structure. We also replaced the very absorptive spiral omitat into a very transparent and high efficiency spiral TDP whole transporter material. As we can see that by developing the vapor deposited spiral TDP, where we were able to achieve less than 10 nanometer spiral TDP compared to more than 100 nanometer of spiral omitat, we reduced the optical losses significantly. And also, because spiral TDP is dopant-free, so that the material also has a potential for higher stability. And by integrating into the solar cell, and together with a bilayer, where we inserted a poly TBD, where we built a cascade energy label, we were able to, again, further improve the performance. And this cascade energy label was important because it reduces the interfacial recombination and improves the whole conductivity. While integrated into the tandem, we were able to achieve 29% efficiency, and this work represents one of the highest for the tandem based on NIP. Okay, I will skip the conclusion because it's already obvious, but here I have already shared a lot of positive, information result for the perovskite field. I hope that's good for the, because we are festive season for Christmas, but I would also emphasize that there are still a lot of challenges for the perovskite and tandem field, particularly for the scalability as well as the stability. Just give you a few numbers, just less than 1 minute. And for the perovskite silicon tandems, the highest efficiency for the small area lab area, 1 square centimeter is 34.9% efficiency. When it scale up to 20 square centimeter, the efficiency is just around 29, so that's around 6% of efficiency loss. With the area 20 square centimeter, that is still at least more than 1 order of magnitude smaller than what is required for commercial products. So we can imagine that how much further efficiency loss that there could be. And also important, these 20% efficiency cells are made with not scalable method. So they are still using some non-scalable method like spin coating in the lab. And that's for the scalability, and the second for the stability. So the best outdoor stability of the perovskite silicon tandems has been tested for 1 year with an initial efficiency of just around 21%, with 20% efficient loss for 1 year outdoor stability test. So that's significant efficient drop. That's far away from the initial efficiency is far away from what we require for the commercial product. And also the degradation rate is much faster than what we need for our commercial products. So we still have a lot of things to do, a long way to go. Okay, with that, I would like to thank for our team member and also our ACAP and also Arena. I'm also welcome for any questions, not only here, but also after in the tea break.